Hello and welcome. This is the Taming Wild AI channel, where we bring AI technologies out of the wild using the best practices of software engineering. In this episode, we're going to look at a slightly more complex neural network model. This one is called LeNet 5. It was introduced by Jan LeCun and his co-authors in a 1998 paper entitled Gradient-Based Learning Applied to Document Recognition. If you do a search for GitHub LeNet 5, the top hit is this repository. There are some positive signs that the owner of this repository has taken steps to tame this model. This is a repository of executable Python code. Contrast this with the previous episode where we encountered an IPython notebook that had to be run inside that web application infrastructure. There is a requirements.txt file documenting a small number of dependencies, and it includes version numbers. This means there is a good chance I can quickly and successfully install dependencies that are compatible with each other using pip install-r requirements.txt. And indeed, this is exactly what the author instructs us to do in the README file. Another positive sign is the very presence of this README file. It includes commands that can be copied and pasted to execute the code. There's also an animated graphic showing the results to expect. If we look at LeNet.py, we see that the code is pretty well organized in a handful of classes. The only thing I don't like to see is these hard-coded configuration values for the different layers. I understand these may have been the values described in the paper, but to bring the model in from the wild, even just to train it on a different data set, we might need to change these numbers. Because they're hard-coded, we'll have to look for them, modify them, and rerun the entire training script. The run.py file is a bit more wild. It has quite a few imports, but it looks like some of these are for the data set. There is code in the global namespace. That tells me this is a script that is expected to execute from the command line. It's not a module you could import for useful classes and functions. That being said, the code does use the if name equals main idiom. Let's clone the repository and see if the code runs the way the author expected. Now I'll create a Python virtual environment to install my dependencies in. Now let's follow the instructions in the README. Looks like it installed everything except Onyx version 1.6.0. Let's try installing the latest version. That works. So let's update the requirements.txt file with version 1.13.0 and then try installing everything again. Now the instructions next say to start the Wisdom server to see a chart of the loss in every epoch. That gave me an error with the pillow package. Let's try installing the latest version of that. (9.4.0). So let's update the requirements.txt file with this version of pillow. All right. Okay, that seems to be working. In the browser, we can see that the Wisdom server is online. In another terminal window, let's start the training script. It's downloading the data, and it seems to be training. And we see the loss in every epoch being charted by the Wisdom server. That took about 8 minutes to achieve 98.86% accuracy in 15 epochs. Now that we have the code doing what the author intended, I'm going to fork the repository and commit my changes to the requirements.txt file. I haven't changed the actual code yet, but I don't want my changes to introduce bugs. That means testing frequently after every change. But a full training run took 8 minutes. My first course of action will be to define a fast unit test that ensures things are generally working, and an integration test that ensures the current functionality, convergence to 99% accuracy after 15 epochs. Let's create a test directory and 2 test scripts, unit.py and integration.py. Now, after starting the training a few times, I noticed that after 10 batches in the first epoch, the loss is around 2.0, but after 30 batches, the loss is consistently below 1.0. After 10 batches, 2.0. After 30 batches, less than 1.0. So let's switch over to VS Code and define a fast test that tests for those 2 conditions. All right, here I am in VS Code, and I have my tests directory and integration.py and unit.py currently empty. So let's now write that test.
Let the code flow.
And let's see if that works. Yep, that runs in about 5 seconds. What I did was I copied some of the imports from my run.py, excluding Wisdom, Onyx, and even Torch. It wasn't necessary. Then I copied the code that defines the training and test data splits. Here is the code that defines the neural network, the loss function, and the optimizer. Then I copied code out of the train function over here that iteratively extracts a batch of training data, computes the loss, and performs the backward pass. I excluded the code that back here, I excluded the code that prints out progress after every 10 batches. And I also excluded the code that sends data for charting to the Wisdom server. Instead, after the first 10 batches, I assert that the loss is almost equal to 2.0. I use loss.item to extract the loss value out of the loss tensor. By specifying 0 decimal places, I allow any loss that rounds to a whole number of 2. After 30 batches, I assert that the loss is less than 1.0, and then I break out of the training loop. Now let's define a long-running integration test that performs a full training.
Let the code flow.
and let's run it. It passes in about 4.5 minutes. What I did was I copied the unit test into this file. I renamed the test more appropriately. This loop iterates over the training set, extracting batches of data. I put it inside of this loop, which performs 15 passes or epochs over the training split. This replicates what was there in run.py. I copied this code from run.py and pasted it here. It performs inference on the test split and uses the results to calculate the model's accuracy. I removed the assertions that were in the unit test up here, and I added an assertion here that the accuracy was 0.99 when rounded to 2 decimal places. This is because that's what was advertised in the README file. By copying code from run.py and pasting it into my tests, I introduced a risk. It's now possible for my test code to differ from run.py. Indeed, it does differ. Run.py prints intermediate progress to the terminal console, as well as reporting it to the Wisdom server. It also saves a copy of the model after each epoch. That's probably why the full training completes successfully in just 4.5 minutes in my integration test, while run.py took 8 minutes. The risk is that both my tests could pass, but run.py could fail in some way. These tests are not comprehensive. They do ensure that the model trains correctly, but they don't test other features of the original code. We're going to mitigate this risk by minimizing the differences between our tests on the one hand and run.py on the other hand. I went ahead and created a new commit with my unit and integration tests. I also added instructions for running the tests to the README file. Now, when I look at run.py, I notice a few things. The main function is where everything should be declared that is going to persist for the duration of the program. Instead, it is almost empty, and several objects are declared in the global namespace. Then there is what might be called an intermingling of concerns, which is the anti-pattern of separation of concerns. This train and test function obviously performs both training and testing, and in fact it also saves this model. We can fix this pretty easily.
Let the code flow.
The train function is supposed to train the model, but it has the additional concern of reporting progress for charting and printing to the console. Cur batch win needs to persist between calls to train, so the author has thrown it into the global namespace. In the interests of separating these concerns, there are a couple of approaches. The object-oriented approach would be to use a callback. So we would put cur batch win and viz into an object, declare it in main, pass that object to train, and then train would pass the loss, the epoch number, and the batch number to a method on that object. The method would then print this information, call the line method on viz, and also update cur batch win. This would separate the concerns of training the model from different ways of reporting progress. A more functional approach would take advantage of Python generators. It would look something like this. So let's copy these objects into main. In this case, train would become a method on the network, and it would become a generator of loss values for a specific epoch and batch number. Generating a series of loss values is an unsurprising thing for a train function to do. The concern of what to do with that loss, epoch number, and batch number gets pulled out of the train function. We can ignore it, we can print it, we can chart it, or we can save the current state of the model. Now let's make this code a reality.
Let the code flow.
Yep, that seems to be working. What I did was I moved all of the training code into a method on the network class. I had to rename the train function because the network superclass already has a train method that I'm not overriding. Inside the inner loop where the original code was reporting progress, I put this yield statement to turn this method into a generator. I did the same thing for the testing code. At the beginning of each epoch, the list of batch numbers and losses had to be emptied. I put that code in main here. At the end of each epoch, we test the model on the test split. We accumulate a cumulative loss and a cumulative number of correct predictions. Then we divide those values by the size of the test split to get an average loss and accuracy. Then we save the model. Every 10 batches, we print out the epoch number, batch number, and loss as before. And every batch, we tell the Wisdom server to draw a line, just as before. Now let's factor the dataset code into its own class.
Let the code flow.
And that seems to be working fine. I simply moved this code into the initializer of the dataset class. The user of this class will need loaders for the train split and the test split, and also the length of the test split. So I exposed these functions using member variables. Then I modified run.py to use this dataset class. Another positive benefit is that run.py no longer depends on mnist, transforms, or data loader. Those dependencies got offloaded to where they belong in the dataset class. We haven't been running unit tests or integration tests. Instead, we ran run.py to observe the start of the training. That's because we didn't change any code that would actually affect the tests. But now we've added two methods to the network class, and we've separated out the dataset class into its own module. Let's modify unit.py and integration.py to use this code.
Let the code flow.
And those seem to work. We moved some code from run.py into the network class. We moved other code into the dataset class. Our tests were already exercising the network class. Now they're also exercising the dataset class. Bottom line is that the tests are better than they were before, even though they're not fully comprehensive. I just added a new git commit for the changes we made. Next, I want to look at the network class called LeNet 5. I noticed earlier that there were a lot of hard-coded values in this module. In fact, the only difference between classes C1 and C2 is a few of these hard-coded values. I would prefer to pass these values as parameters to the initializers of these classes. This helps readability because we can name the parameters to document the meaning and purpose of these different magic numbers. It also generalizes the classes in case we want to use them in other code. I'm going to write tests that define what I want. So I want this to construct this layer with default values. And then I'll assert that those default values have been used. I want optionally to be able to pass a configuration in, and then I'm going to assert that the layer is configured appropriately. I hope you get the idea. These tests will fail now because there is no class named C defined. Let's write similar tests for all of the classes and then modify the LeNet.py module to get them passing.
Let the code flow.
All right, I've added tests for the classes that build the layers of LeNet 5. I've tested the default constructor as well as a configured constructor. In the LeNet 5 code, I was able to replace the C1 and C2 classes with a single C class. And I used the new class in the LeNet 5 code with different configurations to achieve the same result. Along the way, I frequently unit tested the code, and while I was writing code, I ran an integration test in the background. To summarize, we added a fast unit test and an integration test to ensure our model successfully trains despite any future changes. We separated the concerns of reporting progress to the console and the Wisdom server from the concern of training and testing the model. This allows us to use our model code in circumstances where progress reporting or saving the partially trained model are not necessary. Furthermore, if anyone does run into problems with progress reporting, they can fix it with confidence that they won't break model training and testing. We separated the dataset code into a class in its own module. This allows us to reuse the dataset class in other models. It also allows us to substitute a different dataset for this model, as long as it exposes the necessary member variables. Another benefit was that certain dependencies are isolated to the dataset module where they're necessary. We added configurability to the LeNet 5 classes. This adds documentation to the otherwise mysterious layer classes. It helps us experiment with different configurations more easily, and it removed duplication of code. Thanks so much for tuning into this episode. If you found it instructive or useful, please share it with others who might too. Don't forget to click the like and subscribe buttons, and I also welcome all of your constructive comments.